Hello friends, welcome to CEC Live Lectures. Dear friends, with our ongoing series on solid state physics, today we are going to talk on band theory of solids, and for the discussion on the topic we have with us in our studios Dr. Sonia Bansal. Dr. Sonia Bansal is assistant professor in one of the leading universities of the country, and she is a prolific professor who believes in giving her best to the students. She always gives best examples so that the students are benefited. So friends, let's take benefits from her experience too, and let's try to understand this particular theory, that is band theory of solids. Now I would like to welcome our guest Dr. Sonia Bansal once again, and would request her to explain us in detail about this theory. Hello ma'am, welcome to the lecture.
Thank you. Today we will start with the new series, which is the band theory of solid, in which we discuss about the effective mass of the electrons, concept of holes, energy band structure of solids, in which we will discuss about the conductors, insulators and semiconductors. Then we define the band theory, in which we define the Crony-Penny model, we define the difference between these conductor, insulator and semiconductors. Then we define that how semiconductors are used in the band theory, and they are of two types. First is intrinsic and second is extrinsic semiconductors. Then we define the type of diodes which are constructed by using the semiconductor materials, which are the simple diodes and the xenon diodes. First we start with the effective mass of electrons. What is the effective mass of electron? An electron moving in a solid under the influence of the crystal potential is subjected to an electric field. Means when we apply the electric field, then electrons moves in a crystal which is having some potential. Then we expect an external field to accelerate electron by increasing E and K. E is the energy of the electron and K is the propagation constant of the electron, so that it will change its electronic state. Here we define by the diagram that this side we are defining the energy and this time propagation constant. The propagation constant defined when we are taking at the start, then K at the start, and after time t the value of K will be changed, and this parabolic curve we will get. This is the effective mass when we apply the electric field or external field to the electron. Now if we define it in the mathematical form, then E is equal to minus E and capital V. V is the potential, E is the electron. Then dE by dt, which differentiate this energy, is equal to minus E dV by dt, which is equal to minus E dV by dt, and we multiply with the dx and divided with the dx, and we know that this dx by dt is defined by this value. Then dE dk divided by dk dt, means here we multiply with the dk and divided by the dk, and then we have this equation which is equal to minus E dV dx, and that will be equal, that will be multiplied by the nu g, and then n nu g dk by dt is equal to minus E dV by dx Vg. Now d by dt and k is equal to minus E dV by dx. Then we define by d by dt and k is equal to minus E. Then what is A? A is the acceleration because of the external field, which is equal to dVg by dt. Previously we will solve the Vg, the value of Vg we will get from here, and then we will put in this equation. Then after solving we will get this form, so where we have this term which is equal to 1 by me, which is the effective mass, and this is defined the force, which is minus E is equal to F. Then what is the concept of hole in the band theory? What is the concept of hole? Consider a semiconductor to define the concept of hole in a band theory. Then with a small number of the electrons excited from the valence band. This is the valence band and this is the conduction band. And here we are having the electrons at the valence band and they are excited to the conduction band. When the external electric field is applied, then the conduction band electrons will participate in the electrical current. It means the conduction will take place when we apply the external electric field, and the valence electron will move from valence band to the conduction band, and the conduction of the electrons will take place. The valence band electrons can produce the empty states in the valence band, and thus it is contributed for the current. What is the concept of hole? We have defined the, if we describe such changes via the movement of the empty space, means the electrons will move from the valence band to the conduction band and the holes are created, or we can say the empty states are created, the picture will significantly simplify. It means the empty space is called the holes, because now no more electrons are available in the valence band and they are moved into the conduction band and the holes are created, means empty space created. Deficiency of the negative charge can be treated as the positive charge. As the electrons move from the valence band to the conduction band and holes are created, it means negatively charged electrons move to the upper state. Now here we are having the vacancy, and this vacancy will be represented by the positive charge. Holes act as a charge carriers in the sense that electrons from nearby side can move into the hole, means electrons can be moved towards the hole. Holes are usually heavier than the electrons since they depict collective behavior of many electrons. Here we see in the diagram, this is the valence band, which is the filled electronic state. Now a narrow forbidden band in between the valence band and the conduction band. Lower band is the valence band and upper band is the conduction band, and this is represented the electron and this represented the holes. Now this level define the energy, means when the energy given to these applied electric field, energy will be given to the electrons and they will move from the valence band to the conduction band by crossing the narrow forbidden gap. To understand the hole motion, one requires another view of the holes, which represent them as electrons with the negative effective mass, means the electron are having the negative effective mass when they are moving from lower state to the higher state. An example of the movement of the hole, think of a row of chairs occupied by the people with one chair empty. And now move all the people arise all together and move in the one direction. So the empty spots move in the same direction. It means that chair will be empty, means that electrons will be empty and moving in the same direction. Now here we just see the concept of energy band structure of the solids, in which we define the conductor, semiconductor and insulator. In isolated atom, if we consider an atomic structure, the electrons are arranged in the energy level. This is the nucleus containing the positive charge protons, and these levels which is surrounding the nucleus which is represented by the orbits, and this orbital electrons and these orbits having the electrons, and all the levels are filled level. Here we see that this orbital contains the electrons. That's why it is a orbital electrons and they are negatively charged. The nucleus is a positively charged and the electrons which is revolving around the nucleus in orbitals are known as the orbital electrons and they are negatively charged. What is the energy band in a solid? The following bands are important in a solid. Number one is the valence band. Here we see, second is the conduction band, and third is the forbidden energy gap or the forbidden band. If we define a energy band in a solid, then we will define by these three. The lowest is the valence band and the upper is the conduction band, and the difference between these two bands and the gap between these two bands is known as the forbidden energy gap or the forbidden band. Here we see the different states, means insulator. Here we see the valence band and conduction band, the gap is more, means here we are having the forbidden band gap is more in the insulator. If we talk about the semiconductors, here we see the conduction band and valence band are near to each other. And if we talk about the conductor, then they are overlapping each other. It means as we move from the insulator to the conductor, the forbidden band decreases. Conductor is having a very less forbidden band, and insulator having the more energy band gap, or we can say forbidden band. What is a valence band? We are talking about the valence band, conduction band and the forbidden band. First we start with the valence band. What is a valence band? The band of energy occupied by the valence electrons is called the valence band. The electrons in the outermost orbit of an electron are known as the valence electron, and this band may be completely or partially filled. Electron can move from one valence band to the conduction band by application of external energy. Means if we not applying the external energy or external electric field, all the electrons will be in the valence band. It means, and these electrons in the valence band is known as the valence electrons, and it is completely filled or partially filled without applying the external electric field, and these electrons are used for the conduction of the electricity. And then what is a conduction band? The conduction band of energy occupied by the conduction electrons is called the conduction band. This is the uppermost band, and all electrons in the conduction band are the free electrons. That's why they produce the electricity. The conduction band, and they are used for the conduction of the electrons. The conduction band is empty for insulator and partially filled for the conductors. It is empty for the insulator but partially filled for the conductor. Next is forbidden energy gap and forbidden band, which define the three types of bands. Means where we define that it is a material is a semiconductor, it is an insulator or a conductor. Then what is the forbidden energy gap, or we can call it as a forbidden band? The gap between the valence band and the conduction band on energy level diagram are known as forbidden band or the energy gap. Electrons are never found in the gap. Means electrons will be present in the valence band or in the conduction band but not in the forbidden band. Electrons may jump from back and forth from the bottom to the valence band to the top of the conduction band, but they never come to rest in the forbidden band. Means electrons can go from the lower valence band orbit to the upper valence band orbit, or the upper conduction band orbit to the lower conduction band orbit, but never will be in the forbidden band. According to the classical free electron theory, the material can be classified into three types. Number 1 is the conductors, number 2 is the semiconductors, and number 3 is the insulators. What is the conductor? Conductor, there is no forbidden gap. Means the conduction band and valence band are overlap each other. The conduction band and valence band are overlapping each other between, and hence electrons are free to move about. For example, here we see Ag silver, copper, iron, aluminium, like these are the examples of the conductors. Conductors are highly electrical conductivity. So in general, electrical resistivity of the conductor is very low because the resistivity is inversely proportional to the conductivity. So if the conductivity increases, then the resistivity will decrease, and in general we can say the electrical resistivity of the conductor is very low, and it is order of the 10 to power minus 6 ohm centimeter. Due to the absence of the forbidden gap, there is no structure for the holes. Means all the electrons are present. The total current in the conductor is simply a flow of electrons only. For conductors, the energy gap is order of 1.01 electron volt. Then what is a semiconductor? The semiconductors are the material whose electrical resistivity lies between the insulator and conductor. For example, the most commonly used semiconductors are silicon, germanium. The resistivity of the semiconductors lies between 10 to power minus 4 ohm centimeter to 10 to power 3 ohm centimeter at room temperature. At low temperature, the valence band is almost full and the conduction band is almost empty. The forbidden gap is very small but more than that of the conductors, and which is equal to 1 electron volt. Semiconductors behaves like an insulator at low temperature. Means here we define for the 3 temperature. At the room temperature, the resistivity of semiconductor lie between the 10 power minus 4 to the 10 power 3 ohm centimeter, and at the low temperature the conduction band is totally empty and the valence band is filled, and the energy band gap is very small, which is equal to 1 electron volt. And if we talk about the low temperature, the semiconductors at low temperatures behaves like a insulator. The most commonly used semiconductor is the silicon and is having the band gap 1.21 electron volt, and germanium having the band gap of 0.785 electron volt. When the conductor is heated, its resistance increases. The atoms vibrate more and the electrons find it more difficult to move through the conductor, but in a semiconductor, the resistance decreases. The semiconductor resistance decreases. In case of conductor, the resistance increases. In case of semiconductors, resistance decreases with an increase in temperature. It means the electrons can be excited up to the conduction band and the conductivity increases for the semiconductor. And here we see the diagram, the temperature versus resistivity and resistance. Here we see that it is increases, here we see that it is for the semiconductor resistance decreases and increase in the temperature. Insulators. What are the insulators? In insulators, the valence band is full but the conduction band is totally empty. So electrons are free from conduction band is not available. Means all electrons are in the valence band and the conduction band is empty. And in the insulator, the energy gap between the valence band and the conduction band is very large, and it is about approximately 5 electron volt or more. Hence, electrons cannot jump from the valence band to the conduction band. So, a very high energy is required to push the electrons from valence band to the conduction band, and its electrical conductivity is extremely small. It means resistivity will be high. The resistivity of insulator lies between the 10 power 3 to 10 power 17 10 power 3 to 10 power 17 ohm meter at the room temperature, and examples of these insulators are plastic and papers. Now we discuss about the band theory, how we define the band theory for the solid. A useful way to visualize the difference between the conductors, insulator and semiconductor, as we defined earlier, is to plot the available energies for electrons in the material. It means on the basis of energy, we can differentiate between the conductors, insulators and the semiconductors, instead of having the discrete energies as in case of free electrons. The available energy states form the bands. It means we define the conduction, insulator, conductors, insulator and semiconductors by using the bands which define the energy states. The conduction process is whether or not there are electrons in the conduction band. In insulators, electrons in the valence band are separated by the large gap from the conduction band. In conductors like metal, the valence band overlap with the conduction band, and in the semiconductors there is a small enough gap between the valence band and the conduction band that thermal or other excitation can bridge the gap. It means we require some energy to jump the electron from the valence band to the conduction band. With such a small gap, the presence of small percentage of the doping material can increase the conductivity dramatically. It means with such a small gap, we are talking about the semiconductors, the materials can be doped, and by doping some external material in the intrinsic material, then the conductivity of that material will increases. Now here we see the difference between the insulator, semiconductor and conductor by using the diagram. This axis defines the energy of the electron, and here we have the valence band and the conduction band. As we are seeing here, there is a large energy gap. Then insulator at ordinary temperature, no electron reach to the conduction band. But in the semiconductor, the energy band gap is small. The thermal energy can bridge the gap for a small fraction, but in the conduction there is a no gap in the valence and the conduction band, and they almost overlap to each other. Now, what are the difference between the insulator, conductors and the semiconductors? The materials are made up of atoms. As we know, these atoms contribute to the electrical properties of the materials, including its ability to conduct electrical current. It means the atom in a material used to conduct the electric current. For the purpose of discussing electrical properties, an atom can be represented by the valence shell and a core that consist of all the inner shell and the nucleus. It means we define the nucleus as well as the electrons which is revolving around the nucleus. The concept can be understood as a carbon is used in some type of electrical resistors. We notice that the carbon atom has the 4 electrons in the valence shell and the 2 electrons in the inner shell. The nucleus consists of 6 protons and 6 neutrons. So, the 6 indicates the positive charge of the 6 protons. The core has a net charge of 4, 6 for the nucleus, for the 2 inner shell electrons. Then in insulators, we see that an insulator, a material that does not conduct the electrical current under the normal conditions. Most good insulators are compound rather than a single materials. Means we are not considering a pure material, but some materials are doped to represent the insulator, and they are having the very high resistivity. The valence electrons are tightly bound to the atoms, therefore there are very few electrons in the insulator. Example of the insulators are the rubber, plastic, glass, mica and quartz. And if we talk about the conductors, a conductor is a material that easily conducts electrical current. Most metals are good conductors. The best conductors are the single element material. Means pure materials are used as a conductor, like copper, silver, gold, aluminium are the best examples of the conductors, which are characterized by the atoms with only one valence electron, very loosely bound to the atom, and they are free to move to the conduction band. These loosely bound valence electrons become free electrons. Therefore, in the conductive materials, the free electrons are the valence electrons. And semiconductors, a semiconductor is a material that is in between the conductors and the insulators, and its ability to conduct electric current. The semiconductor in its pure intrinsic state is neither a good conductor nor a good insulator. The single element semiconductors are antimony, arsenic, boron, polonium, tellurium, silicon and germanium. These are the examples of semiconductor, and most commonly used semiconductors are the silicon and germanium. The compound semiconductors, the upper we define the pure semiconductor, but the compound semiconductors are also available. That are the gallium arsenide, indium phosphide, gallium nitride, silicon carbide and the silicon germanium are the most commonly used semiconductor in the compound form. The single element semiconductors are characterized by the atom with the 4 valence electrons. Silicon is the most commonly used semiconductor and it is easily available in the nature. On the basis of that, we define the difference between the valence band, conduction band and the forbidden band. Due to intermixing of neighboring electrons energy levels, the permissible energy levels increases. The splitting are so closely spaced, they form a virtual continuum which is called an energy band. The band of energy developed by the splitting the valence electron and occupied by the valence electron is called the valence energy band, or it is called the valence band. May be completely filled or partially filled at any temperature, and it is at the lower state. The permitted energy band next higher to the valence band, and it is called the conduction band, and lowest unfilled energy band, and it may be empty or partially filled. In between the conduction band and the valence band, here we define that there is an energy gap, and that energy gap is the forbidden band or the band gap, which is formed by the series of the closed levels above the top level of the valence band and the below the bottom of the conduction band. The forbidden band is free from electrons, and electrons cannot exist in this band. And here we see from the diagram the energy electron volt energy gap is defined here, and this is semiconductor. This is the valence band, this is the conduction band, this may be empty or partially filled in case of the insulator, and the forbidden energy gap is in between the 0.1 to the 1 electron volt in the semiconductor. And here we see the electron will jump from the valence band to the conduction band by getting the some energy. And these are the examples of the silicon and germanium. The silicon require 1.1 electron volt to jump from the valence band to the conduction band, and germanium requires the 0.7 electron volt to jump from the valence band to the conduction band to overcome the forbidden energy gap. Thank you.
With this note, thank you, ma'am. Thank you so very much for giving us this session. Friends, there is a lot more for you in store. You are requested to be with us as we are back after a short break. Thank you. Hello friends, welcome back to this session. Friends, as you know that today we are talking on band theory of solids, and for the discussion on the topic we have with us in our studios Dr. Sonia Bansal. Dr. Sonia Bansal is an eminent professor, and through her we always get in-depth knowledge on various topics and issues. Let's welcome our guest Dr. Sonia Bansal, and let's try to understand more about band theory of solids. Hello ma'am, welcome to the lecture.
We are talking about the band theory of the solids. Up to now we discuss about the different bands like valence band, conduction band and the forbidden band. Now we define here what is the band gap. When an electron acquires enough additional energy, it can leave the valence shell or the valence band, and it is free to move, and it can excite towards the conduction band. And the difference in the energy between the valence band and the conduction band is called the energy gap. and this energy gap is also called the band gap. Means the energy difference between the valence band and the conduction band is known as the energy gap, or we call it as a band gap. This is the amount of energy that the valence electrons must have in order to jump from the valence band to the conduction band. Once in the conduction band, the electron is free to move throughout the material and it is not tied to any given atom. Now we define the comparison of the semiconductor atom to the conductor atom. What is the difference between the semiconductor atom and the conductor atom? We consider the silicon as a semiconductor and the copper is a conductor. So silicon having the +4 valence electrons and copper has the +1, means silicon atom want more energy to become free than the copper atom here, because the valence electrons are 4, here the valence electrons are 1. Here we see in the silicon, and here this is the copper, this is a 1, and here we are a 1, 2, 3 and 4. Since the copper atom has more energy than silicon because it is far. Here we see that the copper requires a more energy as it is far from the nucleus. Then the silicon, it is as far. Then from the nucleus, then silicon. Here we see that the in case of the copper, this electron, the single electrons or the atoms, it very far from the nucleus. But here in case of silicon, it is very near to the nucleus, from the nucleus, and it is easy to become free for copper atom by acquiring additional energy. Even at the room temperature, they are become free to move. So it is not tightly bound to the nucleus, it is far, so it is easily removed from the valence band to the conduction band. And what is the covalent bond? The silicon atom with its 4 valence electrons shares an electrons with each its 4 neighbors. Here we see that it is having the 4, 1, 2, 3, 4, and it will share by the another electron. This effectively creates the 8 shared valence electron for each atom. It means one atom is shared by the 8 atoms and produce a state of chemical stability. This sharing of the valence electron produces a covalent bond that holds the atom together. Then each valence electron is attracted equally by the 2 adjacent atoms in each share. Here we see that they are attracted equally by the 2 adjacent atoms. Now, the most important topic is the density of state. Density of state defines how much allowed state in any system. Means since the maximum spacing between the consecutive energy level in the solid, and here we define the large number of the discrete energy levels exist in a small interval of energy dE. It means we are considering the energy dE, and in which we are having a different numbers of discrete energy levels only in this dE interval. Each energy level consists of 2 states and each state have only the 1 electron. The energy levels are filled as per Pauli exclusion principles, according to which energy level can accommodate 2 electrons. One is spin up and one is spin down, means oppositely spin electrons can stay, 2 electrons can stay in a single energy level. It means we obey the Pauli exclusion principle. The density of state shows the number of states within a given interval of energy that the electrons may possess. Means we define the energy states where the electrons are filled. If Fe denotes the average number of the electrons that occupy a single quantum state of the energy E, then we define dE be the number of the quantum state of the system whose energy lies in the range of dE, as we consider the case of dE, and we are finding the energy levels, discrete energy levels between the small range of interval dE. So we consider it GE dE be the number of quantum states of the systems whose energy lies between the range of dE. It means the number of electrons of the systems whose energy is in the range of dE will be given by the number of electrons present in the energy range. dE is the NEDE, which is equal to FEGEDE, which is the average number of the electrons, and this is the quantum states of the systems whose energy lies between the dE. It means the number of electrons in the energy range dE is defined by the average number of the electrons that occupy a single quantum state of energy, and this GA is the number of quantum state for the interval dE. Now, Fe defines a distribution function which depends on the probabilities of the distribution of electrons available in n quantum state. We are having a, here we see we are having a n number of quantum states, and we define the distribution of the electrons in these n quantum state by using the distribution function. And GE depends on the quantum state of the system in the energy and can be calculated by using the Schrodinger equation. We see, we consider the small interval E plus dE. N is the number of states and quantum states, and E is their energy, and here we define for the 3 axes, number of electrons in the 3 axes, Nx, Ny and Nz. At each point with the integer value of the coordinate represent an energy state. We are defining energy state in the 3 dimensions also. Now, a spherical surface of the radius n, here we see that this is a spherical surface and the radius of this spherical surface is n, centered on origin known as the radius vector. All points have equal energy known as the constant energy space. Here we define all the points having the constant energy, and that will be defined by the constant energy space. Thus, n represent Nx, Ny and Nz. As we are considering the 3 axes Nx, Ny, Nz, then we can define it as n square, which is equal to Nx square plus Ny square plus Nz square. The number of state is equal to the numerical value of volume expressed in the unit cube of the lattice parameter. Therefore, we can define the number of available states in this shell of octant enclosed between the E and DE. Here we divide this in the octant, and the interval is E, and E plus DE is obtained by dividing the volume of the octant of the shell by the volume associated with a single state, that is defined by the 1 by 8 4 pi square dN by V. What is V? V is the volume of a single state, and this is the volume of the octant. That's why it is divided by the 1 by, it is multiplied by the 1 by 8. The correct number of the possible states is twice, because we are using the Pauli exclusion principle, and the 2 electron can be in the single state. One is spin up and one is spin down. That's why we can take it as plus minus 1 by 2. It means this equation will become the 2 electron in the orbital are in the different state. Therefore, GE denotes the density of state, and in the interval DE, which is equal to 2 multiply for the 2 electron, one is spin up and one is spin down, it will be 1 by 8 4 pi n square dN divided by V. Now here GEDE is equal to pi by V n square dN. An electron within the ionic lattice can be analyzed using the application particle in one-dimensional box. Let the mass of the electron beam is a rigid box of that the mass of the electron will be m in the rigid box of side A is expressed as mass of the electron is m and the side is defined by A, then we can define energy by using the Schrodinger equation, which is equal to n square s square by 8m A square, and we can write it as n square is equal to, and we are calculating the n states, that's why we are taking n square that side, and here n square is equal to 8m A square divided by h square into E. By differentiation, we get 2n dn is equal to 8m A square by h square dE, or we can write it as it as n dn is equal to 4m divided by h square A square dE. By putting the values from the equation 2, 3 and in the equation number 1, we are putting this in this equation, we will get GE dE is equal to pi by V 8m A square E by h square 1 by 2 and 4m A square h square E. First we put the value of n square, then we put the value of n, then we put the value of dn, because here we require the n square and dn, then we put this value here. GEDE is equal to pi by 2 V. By solving this, we will get V is equal to A cube. Volume we will take for this state will be A cube, that will be GEDE is equal to pi by 2 8m by h square 3 by 2 E 1 by 2 dE. That define the GEDE define the state density of state, which depends upon the energy of the energy band gap of the electrons. Now here we see that the pi by 2 8m, the density of state also depend upon the m and also depend upon the energy E. What is the Fermi-Dirac distribution function? The Fermi-Dirac distribution function, as we already discussed, that will be used for the distribution of electrons in the different electronic state. Then we have the Fermi-Dirac distribution function that is derived in an equation in 1926. Independently got the Fermi-Dirac probability distribution function and was given by the Fermi-Dirac. Is governed the distribution of the electron among the different energy levels as a function of temperature. That's why its value is Fe is equal to 1 by 1 plus E bar E minus Ef by kT. What is K is the Boltzmann constant and Ef is the Fermi energy, that is the highest occupied level, can be taken as a reference with which the other energies can be compared. It means the function Fe indicates the probability at particular energy level E occupied by the electrons, means if Fe, the probability of distribution function is equal to 1 if the energy level is filled by electrons. If Fe is equal to 0, it means define the empty energy level and they are not filled. Now here we see that at 0 Kelvin, lower energy levels of the conduction band are occupied by the electrons while upper levels are unoccupied, and this level, which is the last filled level, is known as the Fermi level. This define the distance, define the energy versus graph, and these are the filled state. Below the Fermi level, all the levels are filled. Above the Fermi levels, all the levels are empty. That is defined by the Fermi distribution function and defined by the energy, the graph between the Fermi distribution function and the energy. Here we see at the 0 Kelvin, the probability of the occurrence of the electrons at the lower level are 1, and here we define Ef, the probability of finding the electron in the lower level below the Fermi energy, defined by the value 1. It is clear that the energy level below Ef are occupied while above Ef are unoccupied. So Ef is the maximum energy of the filled level. The Fermi level EF is defined as the highest field energy level in the conductor at the 0 Kelvin, and the Fermi level is the maximum energy that an electron can have in a conductor at absolute 0 temperature. The Fermi level, it means that energy is known as the Fermi energy. Means we define at T is equal to 0 Kelvin for E is less than EF. Energy is less than Fermi energy, and E minus EF is negative, and the exponential function E minus EF by KT becomes equal to minus infinite. So we can take at the 0 Kelvin EF is equal to 1 by 1 plus E power minus infinite is equal to 1 by 1 plus 0 is equal to 1, which represent that EF Fermi distribution function is equal to 1, means all the energy levels below EF are occupied by the electrons. When we consider the second case, when the energy of the other levels are greater than that of the Fermi energy level, then E minus EF is positive, and the function we define by the E minus EF divided by KT, and it will become equal to plus infinite. Therefore, we can write it as Fermi distribution function EF is equal to 1 by 1 plus E power infinite, and we can write it as 1 divided by 1 plus infinite. E power infinite will be infinite, which is equal to 0. It means energy levels are not filled and they are empty. Here we see the charge carrier density, electrons or hole in the intrinsic semiconductor. What is the density of charge carriers which are participating in the conduction of the electrons? The charge carrier concentration is an important tool for the knowledge of conductivity in a semiconductor. In this diagram, we see that the intrinsic semiconductor superimposed with Fermi-Dirac distribution function. At room temperature, in the valence band excited across the forbidden energy gap and enter into the conduction band. As a result, some of the bottom field near EC, bottom field here we define the EC, some of the state near EV are filled with the holes. As this state filled with the electrons and this state filled with the holes when the temperature will be changed. If the conduction band possesses infinite number of energy level, then the density of the electron in the conduction band between the energy E plus dE will be defined by NE is equal to EC, this is the energy of the conduction band to the finite level, ZE FE dE, where FE is the Fermi function which gives the probability of the electron, which we already solved, and then the density energy ZE is the energy density state, and that will be represented by ZE is equal to 4 pi by h cube 2 me square, where me is the effective mass of the electrons and h is the Planck's constant, a power 3 by 2, and E minus EC, energy difference between the conduction band and the other band will 1 by 2. Here we get the equation number 1 and equation number 2, and we define the energy density state, and we already calculated the Fermi function. Then we put these values in this equation 1, where we finding the number of energy levels or the density of electron in the conduction band in the range of energy E and E plus dE. Now the Fermi distribution function will be given by Fe is equal to 1 by E power E minus EF divided by KT plus 1. Putting this value of ZE and Fe in the equation 1, then we have NE is equal to EC approaches to EC to infinite 4 pi h cube 2 me 3 by 2 E minus EC 1 by 2 x, and here we put the value of Fe. Now by solving this, we take the interval between the EC and infinite for this energy level. We take the energy terms this side and then we solve it. After that we know that 4 pi h cube 2 me 3 by 2, which represent the gamma, and its value is 6.82 10 to the power 27 meter cube electron volt, and we put this value here, this constant value here. Then we can write it as gamma for the simplicity, then Ne is equal to gamma and the other part will be the remain same. For energy greater than the Fermi energy, then E minus EF will very greater than KT. Therefore, this term E power E minus EF divided by KT very greater than equal to 1. So we can neglect this equation 5, hence we can write it as Ne is equal to gamma EC2 limit from energy of the conduction band to the infinite, E minus EC1 by 2 E power minus EE KT plus 1 into dE. Then we have this equation. After solving this, we take these two terms this side, AF minus EC, EC minus E. We take this exponent, we divide this exponent into two parts. First is EF minus EC and second is EC minus EKT dE. Then we have here Ne is equal to gamma E power. We take this part this side and take this part with this. Then we know that by putting the EC minus E by KT is equal to X for the simplicity, then dE is equal to KT dX in the equation 6. Then we have Ne gamma E EF minus EC divided by KT EC to infinite KTX power 1 by 2 E power minus XKT dX. If the energy of the band will be equal to the energy of the conduction band and X is equal to 0, or when X is equal to infinite or X is equal to infinite, then we can solve this equation in this manner. Then it will be Ne gamma KT 3 by 2 E power EF minus EC divided by KT, and we take 0 to infinite X power 1 by 2 E minus X. But we know that by solving this by using the standard integral, then we have the result this, and we have result in this form. Then we put this equation in the 4 and we will get we will put the value of gamma from the above equation in this equation. Then we get Ne is equal to 4 pi h square E square 3 by 2 KT power 3 by 2 pi 1 by 2 divided by 2 E power EF minus EC divided by KT, as we are talking about the electrons in the conduction band. Now the concentration of the electrons in the conduction band Ne is equal to 2 pi me square KT divided by S square 3 by 2, and here this is the term for the difference between the Fermi level and the conduction level. And this is free electron density. This is the free electron density in the conduction band of an intrinsic semiconductor, which depends upon the temperature as well as the difference between the energy levels. What is the position of Fermi level in the intrinsic semiconductor? Where the Fermi level lie in the semiconductor? The width of the means the Fermi level, the highest level. What is the position of this highest level if we talk about the semiconductor, on which is the intrinsic semiconductor? Width of the conduction band and the valence band is small as compared to the forbidden energy gap. At energy level in the one band is the same energy. At 0 Kelvin, no conduction, because at 0 Kelvin the valence band is completely filled and the conduction band is completely empty, and the semiconductors behaves like an insulator. Let the temperature increases at T Kelvin, the number of electrons in the conduction band will jump to the valence band. From the conduction band and in the valence band, the total number of from valence band to conduction band, then the total number of N is equal to Nc plus Vv, where the number of the conduction band is given by Nc is equal to Nfec. Then by using this we have Fec is the probability of electrons having the energy, Ec energy of the conduction electrons. Then according to Fermi-Dirac, the probability distribution function Fe is given by FEC and this value. The Fe is the energy of the Fermi level, and T is the temperature, and K is the Boltzmann's constant. And by putting the value of Fe from the equation 2 in the equation 1, we have Nc is equal to N divided by 1 plus E power EC minus EF divided by KT. Similarly, the number of electrons in the valence band NV is defined by NV is equal to N divided by NV minus NF. Then we can write it as N is equal to total number of electrons we defined by the N, which is equal to number of electrons in the conduction band plus the number of electrons in the valence band, and then we have this value. By solving this, by using the formula and we solve this, we have this value in this form, and then lastly we will get E power EC minus EF plus EV minus EF KT. All the terms will cancel out and we have the value of 1. By taking the logarithm of the both sides, we have this value, which is EC plus EV minus 2EF log E is equal to KT log 1, and then we have EC plus EV is equal to 2EF. This EF is the energy of Fermi level is equal to 0, and EF energy of the Fermi level is equal to EC plus EV divided by 2, which represent the Fermi level in the intrinsic semiconductor lies exactly between the middle of the forbidden energy gap between the valence band and the conduction band. This represents that EF is equal to EC plus EV divided by 2, means the band gap in the forbidden energy band gap, the middle band is defined as the Fermi energy band. Thank you.
With this note, thank you ma'am, thank you so very much. Dear friends, if you have any feedbacks or query, do write to us at info.cec@nic.in. We are going to meet again very soon and would be discussing more. Till then, take care. Goodbye. Thank you ma'am, thank you once again.